In this video, we are going to solve optimization problems with the method of Lagrange multipliers. The method of Lagrange multipliers is used to maximize or minimize a function f of xy subject to the constraint g of xy equals 0. So now our constraint is a curve. So we need to find points on this constraint curve for which the function has the highest output and the lowest output. Those are going to be the maximum and minimum values of the function on the constraint. So building off of our absolute extrema, we were restricted to a specific domain, and we had to find on that domain where the function had the largest and smallest outputs. Now we are restricted to a curve. Okay, so that is the difference. And Lagrange multipliers are going to give us a tool to find those points. If we look at the set of level curves below, just to get a visual sense of what we are looking for and how we are finding it, we have a set of level curves for the function f. So the level curves here of f of xy. And notice there the set of lines, okay, labeled up to 5, and then the labels would continue if we need higher values. And then that circle on this set of level curves, that's our constraint curve. So this is g of xy equaling to 0. So there's some constraint function equaling to 0. That gives us a constraint curve. So one curve as opposed to many curves for level curves. Okay, so we want to find the points along this constraint curve for which the function has the largest output and the smallest output. So just by investigating, going around the constraint curve, we should see that right here, the output of the function is 5 because we are tangent to the level curve, k equals 5 for f. And then here, that is going to be an output of 0 because we are tangent to the level curve of 0 for the function f of xy. And those will be the largest and smallest outputs. So we can even write that. So that's going to be the point where the maximum output of the function occurs. And that's going to be the point where the minimum output occurs. Now to give you a sense outside of math of what's going on here, imagine that the set of level curves represents elevation. And we are going on a hike. Okay, so this is a topographic map. And this circular constraint curve is our hiking path. So as we hike along the path, we are going to either increase in elevation or decrease in elevation. And we have a compass that's going to indicate which direction to go in for increasing elevation. And that will be relevant mathematically in a moment. So as we go, we cross different level curves. So here the elevation is 1, then 2, then 3, then 4, then 5. And when we hit that point of tangency, we then head back in the other direction. So now the elevation starts to decrease. So 4, and then 3, and then 2. So that makes that point of tangency the maximum output. And we can reverse the argument for the minimum. As we go down, the elevation decreases, and then hit that point of tangency, and then we start moving in a direction where the elevation increases. So mathematically, what does that compass represent? Right? Because that compass is pointing us in a direction of increasing elevation. Well, if we look at a few points, so right here, if we draw the gradient to f, okay, so that's the gradient of f. And if we draw the gradient of f, and I'm not sure exactly how long these vectors are going to be, they're estimates, okay, gradient of f at the point, gradient of f at the point, gradient of f at the point. So each of these gradients is giving us an indication that we can continue to move along the constraint curve to find higher elevation. Maybe we can't move exactly in the direction of the gradient vector, but we can move somewhat in that direction to increase our function output until we get to this point of tangency. At this point of tangency, the gradient vector is pointing off in this direction, and we cannot move along the hiking trail to increase our elevation in that direction. So that is our point where the maximum output or the maximum elevation is going to occur. Now, if we were to draw in the gradient of g, remember the gradient of g will also be normal to that constraint curve, the circle. So here, right, just for visual, if I drew, so that would be the gradient of g, we could see that they're much different. And I can put more gradients of g, but I don't want to put more on the picture until we get here. Now here, the gradient of g, let's say it's a smaller vector, we don't know that for sure, it could be larger, but just for visual sense, the gradient of g winds up pointing in the same direction as the gradient of f. And right there, that is the key mathematically of why Lagrange multipliers work. At this point of tangency, both the gradient vector of the function f and the gradient vector of the function g wind up being parallel. They could point in opposite directions, so it is the case that the gradient of g could be pointing inward. We would have to know where more level curves of g of xy would be to see where the increasing direction is. But regardless, if it points outward or inward, they are still going to be parallel to one another. And that fact is what unlocks the method of Lagrange multipliers. So hopefully you got a general sense of what we're doing here, right? Finding the points on a hiking trail that would have the highest and the lowest elevation. We talked about having a compass, but the mathematical version is the gradient vector. Having a gradient vector tells us if we can move in a direction that's going to increase our output. Until we get to a point where the gradient vector says go this way to increase your elevation or increase your output, and we cannot move in that direction at all. And then the argument can be reversed for the minimum point. So at a point of tangency, x naught, y naught, the gradient of the function f is parallel to the gradient of the function g. This means for some scalar lambda that the gradient of f at that point of tangency is equal to lambda times the gradient of g. And lambda, that is our Lagrange multiplier. Okay, lambda being the Greek symbol for L. So we have parallel gradient vectors. Lambda is the scalar that makes those two gradient vectors parallel. And this is how we're going to solve for those points. More formally, let f and g be functions of two variables with continuous partial derivatives at every point of some open set containing the smooth curve g of xy equals 0. All right, so basically we just have continuous functions, partial derivatives, and if we drew an open set around the set of level curves and the constraint curve, we're good. Suppose that the function, when restricted to the points on the curve, has a local extremum at the point x naught, y naught, and that the gradient of g is not equal to the 0 vector. Essentially what this part is saying is that the point of tangency is not a critical point of the function g. So it has a derivative, it's not a corner or a cusp or some point that would be an issue. Then there is a number, lambda, called a Lagrange multiplier, for which gradient of f at that point equals lambda times the gradient of g at that point. All right, so this is the formal definition of Lagrange multipliers. Hey, for me, one of the important things is that we are assuming that the gradient of g is not equal to the 0 vector at the point, because then this would not work. To simplify the process of finding extreme values of the function f on the constraint curve, we define the Lagrangian function. So I like to define the Lagrangian function just because then we can build off the methods that we've been using. So we call the Lagrangian function capital F, and we use the three variables, x, y, and lambda. And we create the function by taking f of xy and subtracting lambda times g of xy. Essentially, what we're doing is we are moving this to the other side before we took the derivative, before we took the gradient. So f minus lambda g, that's our Lagrangian function. And then finding the gradient of the Lagrangian function, that's going to be equal to the 0 vector, and that's how we're going to find all the critical points. Once we have our critical points, we're going to plug into the function to see what points give us the largest output, what points give us the smallest output. Sometimes this is easier said than done, so just a couple of pieces to help. Often it is helpful to solve for lambda in each equation and set the expressions for lambda equal and simplify. And this will sometimes give us like y equals x or y equals 2x. And once we have a relationship between x and y, we can plug into the constraint equation to find the critical points. The reason this works often is because we don't care what the value of lambda is. Some applications of Lagrange multipliers, lambda is the important value. For what we are doing, the application we're using, lambda is not an important value and we are not going to be solving for it. We want the critical points and we want to see what the function outputs are at those critical points. And if we must divide an equation by a variable expression, you must consider the case where the variable or variables are equal to 0. This is a little bit hard to wrap your head around without seeing it, but as we go through a few examples, this will make more sense. But essentially, we have to remember we technically cannot divide by variables unless we assume that they are not 0. And we have a way to handle that. So our first example, use Lagrange multipliers to find the maximum and minimum value of f of xy equals 3x plus 2y on the constraint x squared plus y squared equals 13. Okay, so our constraint curve is x squared plus y squared minus 13. Because the assumption we're working off of is we want the constraint curve when it's equal to 0, right? We want that level curve. So we just need to move any constants over to the same side of the equation. Technically, you can do this by saying that it's any constant, but I like the consistency of saying the constraint curve will always be equal to 0. So then we build our Lagrangian. So x, y, lambda. So this is going to be 3x plus 2y, that's our function f of xy, minus lambda, x squared plus y squared minus 13. Okay, so this is f, this is g, f minus lambda g. We take the gradient of the Lagrangian, so partial with respect to x, so that's 3 minus 2 lambda x, partial with respect to y, 2 minus 2, that's a weird looking 2 minus 2 lambda y, and then the partial with respect to lambda, negative x squared plus y squared minus 13. Okay, and remember we're setting this equal to the 0 vector to find our critical points. So that means each component has to be equal to 0. So 3 minus 2 lambda x equals 0. 2 minus 2 lambda y equals 0. And this last component really is just our constraint curve. X squared plus y squared equals 13. Right, so this is really nothing more than the constraint. Which is always helpful to point out because any critical point that we find has to fall on the constraint curve. If we found a critical point that didn't fall on the constraint curve, then it doesn't count. We're only looking for points on this curve that maximize or minimize the function. So here's our first introduction to solving a Lagrange multiplier problem. There are a lot of variables. It can seem overwhelming at times. So let's take the approach of solving for lambda here. So we have 3 equals 2 lambda x. So we'll solve for lambda, so 3 over 2x equals lambda. And then here 2 equals 2 lambda y, so that's going to be 1 over y equals lambda. Now notice, we did divide by a variable. Okay, so we have to consider if x were to be 0, what would happen? So if x were to be 0, then we would have, let's see, all three equations have to be 0, remember. So if we plug into the first part, x is 0, we'd have 3 minus 0 equals 0, which is not true. So in order for this equation to be equal to 0, x cannot be 0. So we're good, x is not 0. Then we have to run through the possibility if y equals 0. So again, all three equations would have to be equal to 0. So if y equals 0, let's just start here. So if y was 0, we'd have 2 minus 0 equals 0. Not true, so y can't be 0. Now, if you got through the first two equations and said, okay, in this equation, x could be 0, that's okay. In this equation, x could be 0, that's okay. And you make your way to the constraint equation, then you would literally plug 0 in for x, solve for y, and those would give you critical points. Okay, so if it doesn't cause an issue and you make your way through each equation and 0 works, and you get to the constraint, then just solve for y, and then there's your critical points. And the same thing if y was 0 and you made your way through, then solve for your critical points. So here we're okay. X can't be 0, y can't be 0. Now we're going to take the two lambdas and set them equal to each other. So 3 over 2x equals 1 over y. So we have 3y equals 2x, or y equals 2/3 x. Okay, so just to save some space, let's go to the next page. So here's our function still, here's our constraint. We established that y equals 2/3 x. Okay, so now what we have to use this for is solving in our constraint. So then we go into our constraint, so we have x squared plus 2/3 x squared equals 13. So x squared plus 4 over 9 x squared equals 13. So 13 over 9 x squared equals 13. X squared equals 9. X equals plus or minus 3. So if x equals 3, that means y equals 2. X equals negative 3. Y equals negative 2. So our critical points are 3, 2, and negative 3, negative 2. So those are points on the constraint curve that potentially maximize or minimize our function. So we plug into our function. So 3, 2, so that's going to be 9 plus 4, so that's 13. And then we have negative 9 minus 4, negative 13. So we have our max and our min. So the maximum value of the function on this constraint curve is 13, and the minimum value of the function on this constraint curve is negative 13. That is your first complete Lagrange multiplier problem. Notice it did take 2 slides in the video just to kind of space out. Some of you might have been able to fit it on 1 slide, but really it's just a systematic approach. It's an algorithmic approach, to use a better term, to finding these critical points. Now find maximum and minimum of 4x squared plus 4xy plus y squared on the constraint 2x squared plus y squared equals 9. Okay, so our constraint g of x, y is 2x squared plus y squared minus 9. Right, that will make that equal to 0. Create our Lagrangian function, so x, y, lambda. So 4x squared plus 4xy plus y squared minus lambda times 2x squared plus y squared minus 9. So gradient is going to be 8x plus 4y minus 4 lambda x, and then 4x plus 2y minus 2 lambda y, and then negative 2x squared, forgot the 2 there, 2x squared plus y squared minus 9. So that has to be equal to the 0 vector to find our critical points. So 8x plus 4y minus 4 lambda x equals 0. 4x plus 2y minus 2 lambda y equals 0. And then this last component is nothing more than the constraint curve, 2x squared plus y squared equals 9. So any critical point has to fall on that constraint curve. Okay, so looking at our first 2 equations, it doesn't look easy. So again, let's try to solve for lambda. So 8x plus 4y equals 4 lambda x. So that's going to be 2x plus y over x equals lambda. And then we have 4x plus 2y equals 2 lambda y. So 2x plus y over y equals lambda. So again, we divided by variables, so just a brief check. So if x were to be 0, so let's go into this first equation. So that would mean we'd have 0 plus 4y minus 0 equals 0. That means y would have to be 0. But if we took the critical point 0, 0 and tried it in the constraint curve, right, 0, 0, not on the constraint. Okay, so no good. Can't be 0. And then if we try this for y, so if y were to be 0, Most likely not going to work out, but let's just show it. So I'll use red this time. So we'd have 4x plus 0 minus 0 equals 0. Means x has to be 0. So same thing, not on the constraint curve, y can't be 0. Okay, so we're okay. We're not missing any critical points by dividing by these variables. And that's ultimately what we are trying to check for, that we are not missing any critical points. Okay, so now we set our lambdas equal to each other. So 2x plus y over x equals 2x plus y over y. So 2xy plus y squared equals 2x squared plus xy. Quadratics, let's get it equal to 0. I'll go everything to the right side. So 2x squared minus xy minus y squared. So we can factor that. So that's 2x and x minus y plus y. So we get y equals negative 2x there, and y equals x here. So we have two cases to consider. The one where y equals negative 2x and the one where y equals x. So let's go to the next slide. Okay, so if y equals x. So if y equals x in the constraint curve, then we have, I'll use a different color, so we have 2x squared plus x squared equals 9. So 3x squared equals 9, x squared equals 3, x equals plus or minus the square root of 3, and if y equals x, that means y equals plus or minus the square root of 3 at the same time. So square root of 3, square root of 3, and negative square root of 3, negative square root of 3. There are the first two critical points. And then if y equals negative 2x, so then we have 2x squared plus negative 2x squared equals 9. So 2x squared plus 4x squared equals 9. 6x squared equals 9. X squared equals 3 over 2. X equals plus or minus the square root of 3 over 2. And then that would mean y equals, let's separate them here. It's going to be a little more difficult to do it all at once. So let's see, x equals square root of 3 over 2. That would mean y equals negative 2 square root of 3 over 2. And x equals negative square root of 3 over 2. Y equals positive 2 square root of 3 over 2. So adding to our list, so square root of 3 over 2, negative 2 square root of 3 over 2, and negative square root of 3 over 2, 2 square root of 3 over 2. Not the nicest critical points that we may find as we do Lagrange multipliers, but nonetheless, they are the critical points. We need to plug them into the function. I've done this ahead of time just to save us some time here. So we get 27 as the output for both rad3, rad3, and negative rad3, negative rad3. And we get 24 as the output for our other two critical points. Okay, so that means that we have a max and a min. Right? Maximum output of 27 occurs at 2 points along the constraint curve, and the minimum output of 24 at 2 of the constraint curves. And actually, I'm not sure about 24. Let's check that. Looks off. So let's see, 4x squared, so that's going to be 3 over 2 times 4. So 4 times 3 over 2. And then minus 8 times 3 over 2. And then y squared, so that's going to be plus 4 times 3 over 2. So 6 minus 12 plus 6. Yeah, knew it was off. That's 0. Okay, at least we caught that before we moved on. Okay. One more example. So use Lagrange multipliers to find the maximum and minimum value of x squared plus y squared plus z squared on the constraint 3x plus 2y plus z equals 21. So here we can expand it to 3 variables. Doesn't really change. Our Lagrangian just adds a variable to it. So our constraint curve is now g of x, y, z equals 3x plus 2y plus z minus 21. So now is a good opportunity for you to pause the video and try on your own and see how you did. I will tell you, you are only going to find one critical point, and we'll talk about why when we get back to going over it. Okay, so I'm going to pick up at the halfway point, so you can see that Lagrangian was created. The gradient of Lagrangian set each component equal to 0, right? Because this is equal to the 0 vector. And we solve, so we got 2x over 3 equals lambda, y equals lambda, and 2z equals lambda. So setting lambdas equal to each other, I got y and z in terms of x. So that's what we see here. Y equals 2x over 3, and z equals x over 3. So now let's go to the next slide where we can substitute for y and z in terms of x and solve for that critical point. So we had 2x over 3 equals y, x over 3 equals z. So in our constraint, we have 3x plus 4x over 3 plus x over 3 equals 21. So that would be 9 plus 1 plus 4, so 14x over 3 equals 21. So x is equal to 9 over 2. Right, 3 over 14, 14, 21, 3, 2, 9 over 2. So if x equals 9 over 2, that means y is equal to 2/3 times 9 over 2. So that's going to be 3. And then z is equal to x over 3. So 1/3 times 9 over 2 is 3/2. Okay, so our critical point is 9 over 2, 3, 3 over 2. And there's only one of them. So the first thing is, even after we evaluate our function, right, so that's going to be 81 over 4 plus 9 over 4. So that's 36. So that's 117, 126 over 4. So 63 over 2. But now, how are we supposed to know if that's a maximum or a minimum? So the first thing we have to do is pick another point along the constraint to evaluate the function at so we can compare, right? So we need a comparison point. So let's say that we have f of 700, right? 700 would be on the constraint curve. The function there would be 49. So that output is larger than the output we got at the critical point. So that means that this is a minimum, right? And just this is another point on the constraint. Now, the reason why we only have one critical point here is this constraint is not closed, right? So in that first slide in the video, we saw a circle which was closed. This constraint is not going to be closed. There are going to be values on this constraint curve that the function can have a higher output at. And we can always find more points that have higher outputs. So the output here is, the maximum output rather, is really unbounded. It can approach infinity. So that means this is the minimum output. And when that happens, one strategy is to pick another critical point on the constraint curve, evaluate, and then compare. Right, compare to the output we got at the constraint, at the critical point rather. Right, and again, it's all based on the constraint curve that we had not being closed. So there's only going to be either a minimum or a maximum. In this case, there's a minimum. Okay, so Lagrange multipliers is really an algorithmic tool to find critical points at which the function can have a maximum or minimum output on a given constraint curve. The algebra can get a bit messy. It can look messy. The best thing for you to do is organize your work, organize your thoughts. All right? Practice more to get comfortable with this method, and we'll see you in the next video.